Okay, and hopefully my laptop does not be weird. Okay, so lecture by request, period 3. Most of the questions were centered around redox reactions and identifying oxidation numbers, then like why do we do them, how do we do half reactions, blah, blah, blah. Yeah, that was pretty much all of it. And then there was some requests for specific balancing in acidic and basic solutions. Yeah. Okay, so our goal by lunch is to get through redox so I can address some stoic questions. Okay? So, help me out by like responding. And if I tell you to be quiet because I need other people to respond, we need to honor that too. So, redox. Why a red pen? When we assign oxidation numbers, and you guys all have textbooks at home, both in the notes and on page 177 in the textbook, there are the rules for assigning redox number or oxidation numbers. In general, and I'm going to summarize, our first rule is that free elements, the oxidation number is 0. This includes elementals, so like argon, cesium, sodium, whatever, as well as diatomic elements, so Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. If it exists by itself, usually it's also bonding with itself, right? It's in its elemental state. It is going to have an oxidation number of 0. Our second one, monatomic ions. Its charge is equal to its oxidation number. Okay, so whatever the charge is on a monatomic, meaning one atom ion, its charge is its oxidation number. Okay. Related to this, because I'm going to go out of order, is ionic compounds. As long as the ions in it are monatomic, the charges are equal to the individual oxidation numbers. So when I say like sodium chloride, sodium has a charge of 1 plus, its oxidation number is +1. Chlorine, -1. Its charge is its oxidation number. Because a thing for oxidation numbers is we're looking at how electrons change through bonding. And assigning oxidation numbers is a way for us to numerically represent how electrons are arranged in a specific compound, and thus how it changes as it undergoes a reaction. So how are electrons changing through a reaction based off of a specific atom in the reaction series? Okay, that makes sense. Okay, so these aren't like real charges, because when I get to compounds, like covalent compounds, they don't have charges, but we're assigning them a number that is technically positive or negative. And I call those their pretend charges, because those are its oxidation numbers based off of how the electrons are changing from how it would exist as an element. And we have rules for that, which we're going over. Rule 4. Yes, it is a 0 in the parentheses. So the charge on a compound, which should be 0, or a polyatomic ion, which actually does have a charge, is equal to the sum of the oxidation numbers in that compound or polyatomic ion. The book isolates groups 1A, 2A in a compound. Take their charge. I'm believing that that's actually tied to ionic compounds right here. And then 6 is an order of assigning all others. It's a priority list right here. So all others in order: fluorine is a -1. Hydrogen is a +1, except if it's alone with metals, it's usually a -1 acting as the anion. So like LiH, lithium hydride, lithium takes the +1 because it's got a higher priority. Hydrogen takes the -1. Oxygen is -2. Except for peroxides like K2O2, this is +1 because that's the previous rule and has priority. That makes oxygen equal to a -1. And that's a potassium peroxide, like hydrogen peroxide. And then from that we have 7A, then 6A, and I'm running out of room, my apologies, then 5A. After that, all others, you're going to use algebra. Making sure you follow higher priority ones. So the priority is highest up at the top and decreases in priority. So like you start at the top and assign starting with number 1 and then work your way down to 6. Okay. If you end up assigning all of them and you have one left and you're like, but that doesn't add to the charge or the 0 for that compound or polyatomic ion. You're like, but that doesn't numerically add up. The charge one, number 4, is higher priority than the assigning of all others, number 6. So you follow the charge one first before you follow the other. And we'll go through some examples. Yes?
Okay, so I kind of have like 2 questions in one. So free elements is priority on number 1.
Uh-huh.
And all others in order is number 6.
Uh-huh.
And fluorine is a free element, but it's number 1. And the diatomic, like...
So fluorine by itself, F2, would be 0. But fluorine in a compound, this is fluorine in a compound like HF, -1 + 1.
So fluorine has to be by itself.
For it to be
By itself,
0.
It has to be diatomic.
Yes.
Okay, because it's more of the half.
Yes, but it has to be by itself.
Okay. So, and like when we added, like even you're saying balance the H's by adding like those elements, those are all going to be +1. Like we said, had 7 H +1 to like balance the H's, because the O's you add water, but the H's you add like just H.
Plus, yeah.
It would be +1.
Those are, because it's already got a charge. So that follows the charge one. Good?
Yeah.
Okay, so assigning oxidation numbers. So some practice. Chromium by itself. This is from page 178 in the textbook if you want to review. Chromium by itself. What is it? No. What is its oxidation state as it's written? 0, because it's a free element. Here we go, moving forward a little bit. What is its oxidation number? +3. Some people have asked me in the past. I haven't gotten it this year because I'm pretty like good about warning you ahead of time. There's a difference between the 3+ and the +3. 3+ is technically for charges. +3 is technically for oxidation numbers. Doesn't matter for the test. Just as long as the sign and the number are correct. We don't care about the order. Cool? Okay. C. For all the ones in the compound, CCl4. So we have 2 in there. So we have chlorine and we have carbon. What does the oxidation number for chlorine have to be? -1. Carbon is lowest priority, right? Because it was not on that rule list at all. It is the lowest priority. It says assign all others using algebra. So we're going to use algebra for carbon. So this has to be a -1 because it's got a higher priority as group 7. Carbon then, we're going to use algebra. So carbon plus 4 chlorines is equal to the overall charge of 0. What's carbon equal to? +4. Good. I like the use of signs. D. Let me know if I'm going too fast, please. Strontium bromide. So we have strontium and we have bromine. Looking at your rules, which rule are we going to use to assign? Is it a free element? Do we have monatomic ions existing on their own? No. This was number 1. This is number 2. This was number 6. 3. It's an ionic compound, right? Strontium's a metal. Bromine is a nonmetal. So this is an ionic compound. So we look up strontium's charge. Can we look up strontium's charge and know it? 2+. How did you figure that out? Group 2A. So +2 oxidation number. What is bromine's? No. It's in a compound. It is not by itself. -1. We are using rule number 3 from the previous slide to do that. The rules might be in a different order if you look at different things because a couple of them flip around. Do they add to 0 as they should? Where's your algebra, bro? That's why Kinsley was getting a little confused because it is BR2, but the 2 doesn't come from it being diatomic. It comes from the rule of 0 charge on an ionic compound or charge balance. Does that make sense, Kinsley?
Yeah, that does.
So if it's part of optical, you would assign it
0. So if I had a different one where I said BR2 liquid, bromine, just bromine,
if it's by itself, you assign it
0.
But if it's part of a group and if it's part of a compound,
You have to follow compound rules. And you got to figure out what type of compound. And it's probably going to get a -1 unless it's a central atom. But there's like, we'll keep reviewing this and practicing as we go through. Because we're going to get into the why do we need to do oxidation numbers here in a second. E, SO3, sulfur and oxygen. Which rule? It's technically, I guess, a combination of 2. 4, because they got to add to 0, and 6 using oxygen. So which one can we assign? Oxygen as a -2. We cannot put a -2 here because that would give us a total of -8 for an overall charge when it should be what? 0. So we're going to use some algebra. So sulfur plus 3 oxygens yield, or should give us 0, because there's no charge on it. What's sulfur? +6. Better? Do we need another one? Maybe one where it's... So which rules? It is not monatomic. It is an ion though. So 4 and not 3. It's not an ionic compound. It is a polyatomic ion. Covalently bonding. So it is starting with 4 because you got to fulfill 4, but you're going to use 6 to start your cell. So which one of these do we assign first? Nitrogen or oxygen? As what? Okay, using algebra, we're going to find nitrogen. So nitrogen plus 3 oxygens has to equal what? -1. What is nitrogen? +5. Good? From the list I made on the previous slide. Okay, why do we do this? So we can determine reduction and oxidation in a redox reaction. So we're going to review some of that. Usually if they ask you what is the oxidation half, what is the reduction half, and there are some, if we had time, practice problems that we could have done, but we took extra on the lab. So as a heads up, they will not explicitly ask you to balance an acidic or basic medium. They will not say do that. They will give you one in either, so you need to be familiar with it. And also, has anybody looked up their college equivalency score to get this whole class covered in college? It's usually a 4 or better to get the whole year, depending on your major. If you're going as an English major, you'll take care of your chemistry requirement, like your science elective, with a 3. Like they'll give it to you for a 3, but your English major. 4, 5. You'll get like, usually your college, like if you go into like transfer requirements or something, they'll give you the AP score, like for whatever college you're going to misassigned. Okay, so I would check, okay? They will usually give you something for a 3, like the lecture, or not usually the lab. They'll usually give you like first semester lecture. Okay, they might give you the lab, but it's usually first semester only for 3. A 4 will vary on your major and your college. Why am I taking this class, Miss Burt? So, you had a question?
Yeah. What if you do that for an acidic? Is it like wrong?
Technically, yes, because like, so acid versus base, yes, it would technically be that, like, be wrong. Somebody asked, when would I need to know, like, would it be clear? They would be very clear if you needed to do something in acid or basic solution, just like I did on that worksheet. However, like determining if it's in acidic or basic media, like solutions, if it's an acidic solution or a basic solution, how do you know if something's acidic? No. Hydrogen ions or hydronium, right? So if we're talking about an acid, yeah. What? Base. So leading H is an acid, where A can be anything after. Leading H is an acid, donates a proton. The notes. A base has a hydroxide ion. So sometimes shorthand we write it as BOH, base being anything kind of in front. It is a proton acceptor because the OH accepts the proton and becomes what? Water. That's a neutralization reaction. That's why water is considered a neutral solution, though water itself can act as both an acid or a base, accepting or donating a proton, depending on what it's mixing with, called amphoteric.
So this is always the case, like you'll always have OH or base.
When we get, so for right now, yes, we're going to get into acids and bases in more depth in Unit 8. I think it's Unit 8. Yes, Unit 8. And then we start talking about weak acids and weak bases. The proton acceptor and proton donator is the key thing when we get to Unit 8.
So right now it's almost
This works here, yes. Good?
I already know I'm gonna cry. I'm gonna get probably about very on this.
There's 13 multiple choice questions and 2 FRQs. It is short. It's timed at 50 minutes. Okay. Redox reactions. In acidic media or solution. Why do we use oxidation numbers? It makes it very obvious where our 2 half reactions at, because those are the 2 atoms that's their oxidation numbers are changing. So it makes it easy for us to identify the 2 half reactions before we start balancing it. Okay, ready? Okay, assign your oxidation numbers. Copper solid has what? 0. Nitrogen and oxygen, which one can we easily assign first? As what? -2. So what's nitrogen? +5. 3 times -2 is -6. Got to add to -1. So +5 does that for us. Copper ion. +2. Ions take their charge for their oxidation number. Nitrogen dioxide. Which one do we know? As? Okay, then what does nitrogen have to be? +4. Yeah, because there's 2. So 2 times -2 is -4. +4 gives us 0. Good there? Yeah? Okay. Which ones are changing? Which atoms are changing? Nitrogen. So there's 1 half reaction. Copper. Okay. Which one is, because this is a valid question. Yes, Justina, sorry. Partly the amount of oxygen. So when we write, so for this one, we would do nitrogen +3 oxygen has to add to -1. So it's a combination of how many oxygen there are and the overall charge on the species we're looking at. If we look on this side, it's nitrogen +2 oxygen, and that has to combine to give us 0 because it has no charge on that one. That makes sense? Okay. So that's the post rule 6, use algebra to figure out the rest. Okay. Good. Okay. Which ones are reduction half? Which ones are oxidation half? Say what?
Oh wait, no, it's positive, so it loses.
It is our oxidation half, but it is not gaining anything. Leo says GER. Loss of electrons is oxidation. Gain of electrons is reduction. Alternatively, we have oil rig. Oxidation is loss. Reduction is gain. They're mnemonics to remember. Pick one. What?
Oxidation is losing redox.
Mm-hmm.
So is the copper oxidation and
Uh-huh. Reduction is the easier one. And when we talk about being oxidized or reduced, we are looking at the overall oxidation state changing, the number. Reduction is a little bit easier to figure out because if I say you're reducing the oxidation state on that, are you expecting it to become more positive or more negative? If you were reducing something, you'd expect it, number sense, to be more negative. Gaining electrons is a negative change. So it will become more negative, so it's a reduction. So what I would suggest is identify your reduction first, because what does the other one have to be? Because they're always coupled. When one gains, the other has to lose. Okay? So, reduction. Do you actually get it, Elizabeth, or are you just like into this? Reduction. Which nitrogen or copper is being reduced? Nitrogen, right? +5 to +4. That is becoming more negative. It is being reduced. It is the one gaining electrons. So the other one must be oxidation. Checking, oxidation is a loss. So losing electrons is an overall positive change. Cool? Okay. So now we've identified the two halves, which is an applicable AP question. Now to understand how acidic basic solutions work, you may just want to practice being a sponge and absorbing. Okay?
that's what I'm trying to start.
Oops. Copper makes copper ion. And then I'm going to review the rules. I'm not going to write them down. We are doing this in acidic conditions. We'll do a base. We can do another acid one later, but we'll do base next. Okay, acid conditions. Your first step is to balance all non-hydrogen, non-oxygen atoms. So save hydrogen and oxygen for last. Are they balanced? Hard work. Yes. They are both balanced, so we don't have to do that. Now we're going to balance which one first, hydrogen or oxygen? Oxygen first with what? Water. Left-hand reaction, do we need to? No. Right-hand reaction. Product side. How many waters? Good. Okay. Balance oxygen with water. Balance hydrogen with what? Hydrogen ions. Ions, not atoms. Okay. Just make sure we remember that charge because it comes into play in the next step. So I have hydrogen here. On this side, what am I adding?
That makes sense.
Good. Okay, your last step before you now check stoichiometry is to balance charges. With what? Okay, electrons are what charge? Negative. So if I have 0 and +2, where are those electrons going? Product side, so +2 electrons, and I don't have enough room there. I'm going to get rid of the state of matter. +2 electrons. Yeah? Notice my oxidation half reaction makes or produces or gives up, loses electrons. So it's a way to check oxidation. It should be a product for your electrons. And then now we have plus a -2 charge from this one. 2 electrons gives it to 0. Make sense? Okay, I'm going to erase that then. On the other side, 2 positive ones plus a -1 has to equal 0. Do they equal? No, what's this charge total? +1, so what am I doing? Okay, good. Notice my electrons are on opposite sides of the reaction for each half reaction. They're on opposite sides. That should happen because our end goal is that we eliminate them totally. Can we eliminate them as they stand? No, so we need to multiply by coefficients to make them the same. Do we need to change, the left-hand one? No, to change the right-hand one by multiplying, I hear you guys whispering it, by 2. And since it's already balanced, the right-hand reaction is already balanced for itself, to only change its stoichiometry, we multiply everything by 2. So it stays balanced, but now we can eliminate the electrons. Does that make sense? Yes. Okay. So multiplying everything by 2, and I'm going to rewrite it, but over here, 2 electrons plus 4 hydrogens plus 2 nitrates yields 2 nitrogen dioxides plus 2 waters. And now I can combine these 2 reactions. I stacked them so it's easy to see. When you combine 2 reactions, what do?
You cancel out.
Cancel out or simplify, because do they always cancel fully out?
No.
No, but you can simplify so you don't have like random water on both sides. So the electrons cancel. Does anything else? No. So we write what's left over. And no, it doesn't matter which order you write it in as long as it's on the right side and it is simplified. And that's it.
Is there a reason why you wrote the state on the copper?
I could write the others.
But there's no, like, you don't have to do that.
No. Oops, that should be it too. The AP test won't take off points for that. Will Miss Burt? Probably. In the balancing half reactions, like the redox reactions, probably not, but you need to make sure you pay attention to include your charges. What's up? You're thinking really hard, Peyton. Okay. Lunch is in one solution. Oh, did we still need that?
No, I haven't.
Sup?
We could technically go from the one we had in the acid solution and turn that into a basic solution.
Technically, yeah, but half the time it doesn't work out very well. Because usually based off of transfers of electrons, things happen different. It's easier to go with one that I know is supposed to work in basic solution and go from there. So, they'll tell you. If you're balancing an acidic or basic solution, they'll tell you. If like they ask you, is this an acidic or basic solution? You'll be given this. What'll tell you that this is an acidic solution? Now, if it was a basic solution and you're like, instead it would be written as going off of Riley's comment, oops, It'll be written as that. What tells you it's basic? Cool. And yeah, Riley, I did that in my head. I would not recommend that because my brain hurts.
Okay, because you added balance to your far side and then only two. Wouldn't that be 4H2?
It is. So this is 4H2O. These cancel, making this 2. Because you have water on both sides. And that's how you do basic conditions if you forget to do it until the very end. Which that one works. Like, you can do it that way if you prefer. Do we want an easy basic or a harder basic? This is number 8 from your worksheet. I think it's number 8. Yeah, that one's hard. Okay. IO3 minus plus RE yields ReO4 1 minus plus fart. Ready? Rhenium. Mm-hmm. It's on the periodic table somewhere. Okay, assigning your oxidation numbers. First one, iodate ion. Which one's easy? Oxygen has what? -2. So what does iodine have to be? +5. So that way you end up with a negative overall charge. What is rhenium then? 0. In the other compound, what is rhenium? Well, what's the easy one? Oxygen. What does rhenium have to be then? +7. On the other side, what is oxygen? And iodine? Look at how fast y'all did that. Anybody stuck, confused, crazy? We're all crazy. We good? Bailey? Do I need to go over it? Or over one of them? Okay. Which ones are changing? Okay, there's one half reaction is the iodine. The other half reaction is rhenium. Right, notice what's not changing is oxygen. Sometimes oxygen does change, but not in this case. But this makes it easy. Which one is being reduced? We said that's the easy one to identify. Iodine, because it's going from +5 to +1. So this is our reduction half. Which one's our oxidation half? Rhenium, the other one. And checking 0 to +7, yeah, we're losing electrons there. That makes sense. Becoming more positive, less negatives. Cool. Okay, splitting into half reactions because we're doing this in basic. IO3 minus yields IO minus, and then rhenium. Re yields ReO4 minus. First step is to balance what? No. Everything but oxygen and hydrogen. Are they balanced? Yes. So our next step is to balance what? With what? Okay, left-hand reaction. Where am I adding water? Products. How many? 2. Cool. Other side. Where are we adding it? Reactant side. How many? Okay. Continuing on after lunch. Okay. So we added water to the right-hand reaction. Now we need to balance the hydrogens with what? Hydrogen ions. So for the left-hand reaction, how many am I adding? 4 to which side? The reactants. No food coma yet, guys. Come on. Okay, for the right-hand reaction, which side am I adding? Products, how many? Uh-huh. It's okay. It is basic solution. You can't keep the acid. How do you neutralize acid? With base. You neutralize acid with base, which is hydroxide ion. So to make both of these basic, we're going to add hydroxide to both sides in order to neutralize the acid. Ready? So I have acid here. I'm going to add 4OH. So this becomes 4H2O instead of this. So I'm going to cross this off. But I have to do it to the other side too. So I'm kind of running out of room. Plus 4OH, because our atoms are balanced. So if we do it to one side and the other, there's no change, no net change. It's still balanced. I repeat this with the other one. So I add 8OH to both sides, and I don't have enough room. This becomes what? 8H2O. Cool. And then that goes away. Cool. I'm going to rewrite these a little more cleanly because this looks like a hot mess. So 4H2O plus IO3 minus yields IO minus plus 2H. Ooh, can I simplify that? I have water on both sides. Can I? What's my net water? 2 on which side? The reactant side. So this technically cancels out and there's 2 left. So I have a 2 here. So I don't need that. So plus 4OH. We good there? Okay, continuing to the other side. Uh-huh. At the end, it should be simplified. So if you save that for the very end, that reducing, like if you notice, oh, I have water on both sides and reduce it in your final answer, it's fine. As long as your final answer is the correct answer. It doesn't matter where you simplify, as long as you do. Cool? Now, the right-hand one, can I simplify anything before rewriting it? Right? So this cancels, and how many am I left with? 4. So I have 8OH minus plus RE yields ReO4 minus plus 4H2O. My last step before I start getting them ready to combine is to balance charge. -1, -5. Which side needs more electrons? Reactant, how many? Other one. What's the total charge on the reactant side? This side, what's the total charge? -8. On the product side, -1, because there's only one of these negative charges and there's no charge here. So which side needs electrons? How many? Good so far? Which one? The charge? 8 times -1 is -8. ReO4 with a 1 minus. Oh, you mean the left reaction? Hold on. Okay, this side. Before I added the 4 electrons, 0 plus -1 is -1. -1 plus 4 times -1 is -5. Good? Now check your electrons. Are they equal? No. What's the easiest way to make them equal? Multiply them by each other. This is one of the ones I picked, why I picked it. It's okay that they're big numbers. It happens. It might throw you off and freak you out. Okay, so I'm going to do the left one first, and I'm going to stack them. So 7 times 4 is 28 electrons, plus 14 water, plus 7 IO3 minus yields 7 IO minus plus 28 hydroxide. The other side, 32 hydroxide plus 4 rhenium yields 4 ReO4. Sorry, the long arrow is making me giggle. 16 water and 28 electrons. Here's where we simplify. What cancels? So we're going to add them together. We cancel first. What cancels out? Obviously, the electrons. That was the goal with those really massive numbers. What can we simplify? The water and the OH. So start with water. Which one cancels? 14, leaving me with how many left? Hydroxide, which cancels? 28, leaving me with how many? Right, what's left? So 7IO3, doesn't matter which order? No, as long as it's on the correct side. Done.
You're combining the stuff from the reverse side.
That's why I tried to put the arrow down the middle so I can see the left and the right.
I did the like electron part before the OH. They got the same thing. Does that matter? Because like in the notes, or somewhere, I don't know.
I usually do the.
About how like it said before to do everything the same and then add the OH, because I did it the same way she did, because
Okay.
it said to do the exact same way
Okay.
and then add it. So that's
I'm going off of memory. So
I don't know the other way.
it's fine. As I showed, what was it, this one? Right, you can do the hydroxide after. You're technically adding 4 negative charges to both sides in this one. You're technically going to add the same number of negative charges to both sides, so it shouldn't change your electron or charge count. So you can do it as though it's acidic solution until you get your final balanced answer, and then swap it for base. That makes sense? Questions? I don't know, how does it do it in the textbook? Textbook does it my way. This way. But they all work out, right? It's like a addition order, like in math, like it doesn't matter which order you add stuff in, because you're going to get the same number at the end anyways. Now, if you're doing multiplication and addition, that's different. So
when I'm just trying to like, I kind of
Process.
where we went from the H to the OH.
Mhm.
So where you see an H, you just add the same amount of OHs and it just equals out to makes it H.
that same water.
Okay.
Because what is water? Right? H bonded to an OH. That is why water, and it should have been in your notes, is amphoteric.
So basic is
Well, it is able to act as a base and accept a proton, which when it does that, it becomes H3O plus, adding a proton. It can also act as an acid and donate that H plus and is left with its conjugate base. Good? Why are you looking at me like that?
I don't know where this.
It makes sense.
Sidebar stuff. Okay. Becca, did you have, I see your hand. Did you have an example of the using a fraction to balance stuff problem?
No, I thought I did, but I just couldn't do it. Realized I didn't really know how to do it.
Okay, this might work.
You can do that too.
Huh?
You can do the fraction and then multiply it by the denominator for that too.
You could, it's usually just for diatomics. So I wouldn't do it unless like it looks obvious that that is a way to fix it. We can.
Just when you were saying
Hold on, there's like 30 people asking. Kinsley first. Did you have anything to finish regular stoic beyond that?
no, I was just asking if you were like when you were saying about the fractions, were you implying that you were going to do that first?
Well, there was a question on how do you balance with fractions, and that's what I was going to address. We can move into stoic if we want. No, just double the first and then keep going. Ready?
Yeah.
Okay, which number is this?
This is made up from Miss Bert's brain. Dang it, that's not going to work. Hold on. No. Or okay, there we go. Sorry, having to do math in my head, not great. This is just how do you balance a chemical reaction when the math isn't mathin'. Ready? Math isn't mathin'. Let's review some balancing strategies. Identify your elements or atoms. Take inventory. Shush. Peyton. If it's by NIDA, I'm not surprised. Please don't start stuff in my classroom because I'll finish it. 1 goes into 4. 4 times. 4. 8 plus 1 is 9. 2 goes into 10. 5 times. So 8 plus 5 is, whoops, that's 13. No, yes. And then 10 for that. Oh no, that math doesn't work. Right? 2 doesn't go into 13. Well, great news is that 13 over 2, we're saying divide this in half, and then we have 13 oxygen. Right? Uh-huh. Can you keep it, though? How do you get rid of the fraction? I showed you guys last year. I'm sorry you didn't pay attention. I'm pretty sure the video's recorded. You just have to hunt through like the 150 videos I have on my YouTube channel.
I tried. I tried.
Becca,
Yeah, subscribe.
that help? Okay.
Subscribe to Bird Killer. You get it.
Trying to make money off of YouTube. Subscribers.
Do you make money off your YouTube channel?
No, not at all.
I think you should. Like, set it up.
Yeah, we should start promoting you. Oh my gosh, stop monetizing it.
All like 47 of my followers.
I like them.
I know you know the number off the top of your
You get
head.
that monthly.
I need to go back, hear your voice tonight, because that's not creepy. Okay. Arsenic. Let's check its oxidation states. It's 0 here. +1, -2. What is it in this one? I mean, if you stare at it for a second. It works, right? Algebra. Ready? Can I erase?
No. Please no.
Okay, next. Arsenic hydride. What does hydrogen have to be? Nope.
+3. Oh.
It's that exception that we talked about, like when it's with, like, technically arsenic's a metalloid, plays both parties. Oh no, wait. No, my bad. It is +1. Miss Burke can't math. So -3. Cool. My bad. I can't math. Or pay attention to a periodic table. It is a metalloid, but that doesn't work out. Ready? So arsenic is doing what? And losing. So 1/2 reaction. And then the other half reaction. Holly, could you do it now? It's tricky. I will admit it is tricky. Anyone else? Could you balance it following the steps for acidic solution now? Yes. Right? It's just funky. Because arsenic is double dipping.
No. Go. Yeah.